And we're so thankful, Swati, that you've been able to join us tonight. Just a little background about her. She got her bachelor's at Cornell and soon after joined JPL. I think that was in like 2004, early 2000s. She worked on the Cassini mission with the Huygens probe to Titan. Super cool mission. I mean, I still have visions of the lander that took images of Titan. Just incredible. Went back to school, MIT, got her PhD in aeronautics and astronautics, and then went back to JPL and became the lead guidance and control officer, system engineer for the Mars Perseverance mission, and directed the cruise and all the way through landing. Just totally amazing work. And I still get goosebumps watching that video. You know, both the one where it's actually, you don't know if it's successful or not, and then the one with the actual onboard video from the lander. Crazy, super cool. Nobody does it better. And Dr. Mohan was part of that, right front and center. So welcome to our general meeting for NOVAC. We applaud your efforts and thank you for being here. And I will turn it over to you.
Thank you for having me. I'm going to give a talk today that starts from like the highest level of why we're exploring Mars and kind of gets more and more in depth and with some of the technical details. And hopefully it should run about 30 to 40 minutes and there'll be time for questions afterwards. Let's make sure. Here we go. Do you see my screen? Yep. Okay.
Yes, it's coming through fine. Thank you.
Perfect. Okay, so Mars 2020. This is not the first mission that we've sent to Mars. So why Mars? You know, in the late 90s, NASA developed this strategic vision of how they wanted to explore Mars. Mars is our closest neighbor, and it has a lot of the same features that we see on Earth. The idea was, first and foremost, to follow the water. The idea being water here on Earth accounts for almost all life. All life is, 90% of life is within like an hour from some source of water. So the idea was if we could find water on Mars, that may lead us to whether or not there was life on Mars. So the early missions starting in the late 90s really built on that with a series of landers, orbiters, rovers, kind of culminating in the Mars Science Laboratory, which was the Curiosity rover in 2011. The buildup of all of those missions through Curiosity were able to definitively find evidence of water on Mars, current liquid water on Mars. Once we were able to do that, the additional science instruments on Curiosity started trying to find the building blocks for life. It's not just water that we need, but it's water in conjunction with different elemental building blocks, carbon, nitrogen, hydrogen, oxygen. Were those building blocks there for life? So if you can find the water itself and you can find those elemental building blocks for life that life requires, then you have a chance to find life itself. So with the culminating the Curiosity mission around 2011, the scientific discoveries led us to believe that yes, water has been discovered on Mars, as have all the building blocks for life. So now the Mars 2020 mission is going to the next step. We know that Mars was once a place that had liquid water, that has those features for it. So can we actually find the evidence of past life on Mars? We're specifically going to an area that we believe was habitable and taking the equipment to find the signs of past life. Now, this isn't, you know, little green men or even fossils that we think of here on Earth, but rock features or geologic features that would only have been created by processes driven by life, not by things like erosion whether by air erosion or water erosion, but actual formations of rock features that can only be created by life. And the idea is if we can go to this type of habitable place, there's only a limited set that you can bring, a limited set of instruments that you can bring all the way from Earth to Mars. So what we really need to do to answer the question of whether or not there is life on Mars is to bring back the samples from Mars that we think could have the signs of life to Earth. Once we are able to bring back those samples and unleash the full arsenal of Earth scientific laboratories and equipment, that's when we'd be able to definitively say whether those samples do have proof that there was ancient life on Mars. So Mars 2020 was tasked as that first leg of sample return. So its job is to actually go to what we believe is a very habitable place in the past on Mars and actually collect samples for retrieval one day back to Earth in the hopes of answering that question of whether or not there was past life on Mars. Now, Perseverance in Mars 2020 was not the first rover to go to Mars. The first rover was actually Sojourner back in 1997, along with a Mars Pathfinder mission. Each of these rovers kind of evolved. Sojourner was a technology demonstration. You know, nobody had done rovers back then. We didn't know what the surface of Mars was like, whether it was hard enough to actually allow wheeled traversing. So Sojourner was a tiny, like cereal box type rover that was intended just to go 100 feet or so from its parent ship of Pathfinder. But the demonstration of Sojourner allowed us this wonderful advancement of how to explore on Mars. So after the success of Sojourner, we built the twin rovers of Spirit and Opportunity. And after that came Curiosity. Now, Sojourner and Spirit and Opportunity were still fairly small size. Curiosity and Perseverance is about the same size as Curiosity, or about an order of magnitude bigger than Spirit and Opportunity. So we had to evolve what the technology was to land on Mars between Spirit and Opportunity and Curiosity. So for Spirit and Opportunity, it was the architecture of what entry, descent, and landing was basically to wrap the whole rover lander in bubble wrap, basically. So we come in after separating with the crew stage, deploy a parachute to slow us down. It doesn't slow us down quite enough, so we inflate these balloons around the rover, cut the bridle, and drop the balloon encased spacecraft, and it just drops and bounces. Eventually, the gravity of Mars and the loss of that kinetic energy allows it to come to rest. Once the spacecraft detects that it's at rest, it pops the balloons from the inside, lets them deflate, and then drives off. Now, we tried to apply the same bubble wrap architecture to Curiosity, but it didn't work. There was no way the material for these inflatable balloons would be strong enough to hold the Curiosity rover. Curiosity and Perseverance are fundamentally bigger, and the weight of dropping them even with the bubble encrusted was tearing the bubble wrap. It was not protective enough for that. So we had to develop a new entry, descent, and landing mechanism for Curiosity, which was the sky crane entry, descent, and landing mechanism, where we, instead of dropping them encased in bubble wrap, we basically lower the rover on its wheels through a bridle until its wheels down on the ground, then cut the bridle and deflate. Now, Perseverance borrows heavily from Curiosity's entry, descent, and landing, but there was a couple of big upgrades that we had to do for Perseverance that were entirely driven by where we wanted to go on Mars. So Spirit, Opportunity, and even Curiosity, they had landing sites that we think of as like parking lot landing sites. They're not the exact scientific area that you want to go to, but they're the nice, flat, safe region next to the scientific area of interest. So they were really safe, but then you had to drive all this way to get to the actual area of interest. That wasn't going to work for Perseverance. So Perseverance, as the first leg of Mars sample return, was headed for Jezero Crater. And this is an image of Jezero Crater. You can see that it looks like an ancient lake, a riverbed. There's this beautiful inflow channel that would have been a river culminating this delta that basically shows us that Jezero Crater looks like an ancient lake on Mars, where this is kind of the cusp of that caldera with the inflow channel. And lakes are great places for housing that biological material. You have the different regimes of down here on the lake bed, you have the actual hills themselves or the river inflow channel. So there's a lot of scientific information here, perfect for a sample return mission, because you can actually drive to multiple different sites that have slightly different geologic features to be able to collect samples. That's all fantastic in terms of the scientific value of this site. The problem is all of these things that look great to the scientists are things that make us engineers cringe. You know, this hill here is basically like a 800-foot cliff right in the middle of the landing ellipse, which is this white circle here. We had different crater walls here, sand pits kind of in this area that if we landed there, we couldn't drive out of. Sorry, this is the cliff that's kind of in the middle of the landing site with the craters. And then the region here, though it looks kind of smooth, is actually littered with rock fields. So this is by far the most hazardous region we've ever attempted to land on Mars. And we needed to make sure that we could still land there safely enough, similar to the previous missions. So that landing site actually drove a lot of innovation for Perseverance to allow it to see the hazards of where it was landing and find the spot that it wanted to go to within this ellipse that would be the safest. So we started working on the Mars 2020 mission very shortly after Curiosity landed successfully. So Curiosity landed in about 2011. So about late 2012, early 2013, we started working on the Mars 2020 mission. And they named it Mars 2020, you know, gave us a very strict goal to work with, because the Earth and Mars periodicity happens such that every 26 months they line up to create the shortest transit from Earth to Mars. So we knew, you know, back in 2012 that we were aiming for the launch window in 2020. The mission itself is broken up into 4 main phases. So you have the launch of getting off the surface of the Earth into space. You have the cruise and approach. So this is the entire journey from Earth to Mars. This lasts about 6.5 months. We have entry, descent, and landing, which roughly lasts for about 7 minutes from the top of the atmosphere down to the ground. And then we have the surface mission. This is the actual important part of the Perseverance mission, of actually going around and doing the science and collecting it. And that's slated to last about 1.5 Mars years, which is 3 Earth years. And it had, yeah, so 3 Earth years as the minimum of how long that surface mission lasts. So just a few cool pictures of the Mars 2020 spacecraft. This is the spacecraft in one of the final photos at Kennedy Space Center before it was put into the launch fairing. So it has multiple different parts. The rover itself, which you can see is kind of buttoned up with its like legs folded in, is this part right here, kind of tucked up into the air shell. Wrapped around it is all of the different hardware that is required to actually get it to the surface of Mars. So starting at the top here, this is the cruise stage. This is the part with all the tanks and sensors that measure it to get from Earth to Mars. Once we get near Mars itself, about 10 minutes out from the entry to the Martian surface, we jettison this top cylindrical part. And after that, we come in as a capsule of this whole entity. So this part is the back shell. It holds the parachute of the vehicle. You can see the white areas here. The bottom part here is the heat shield. That's what protects us from all of the plasma and the heat as we come screaming into the Martian atmosphere, and dissipates a lot of that heat. Once we're far enough into the Martian atmosphere, we jettison the parachute out of here. We come in on the parachute. Once we're on the parachute, we don't need the heat shield anymore because we're glowing slowly enough, about 120 meters per second. So we jettison the heat shield. That allows our sensor to see the ground. The rover itself is tucked up with its jetpack, which is called the Powered Descent Vehicle. This is the jetpack that basically allows it to fly out the remaining distance. So we come in on the parachute. It gets to terminal velocity, which is still higher than what we'd like to land. So we eventually cut the back shell out and come in on the retro rockets of the jetpack that's kind of hovering in it. So that allows us to go all the way to the selected landing site, and then the jetpack hovers while it lowers the rover itself down on a set of bridles. That's the sky crane maneuver, until the rover's wheels touch down on the ground, and then the jetpack cuts the bridles and it goes off and crashes elsewhere on Mars. So out of all of this hardware, the only thing that survives on Mars is the rover itself. So to give context of the scale of this, this is the entire Mars 2020 spacecraft in the top of the launch vehicle fairing that it's about to get put into. There's a couple of markers here, like this part is a filing cabinet. So you can think of a person as about half the size of that filing cabinet. So that gives you a context of how big the spacecraft is, and then how big the launch vehicle fairing is. We ended up launching at the end of July in 2020, right in the start of the pandemic, which was a really stressful, interesting time. We had one of the quickest cruises from Earth to Mars. We launched about a couple weeks into our launch window on the first day that we attempted, and that was like July 30th or 31st maybe. And then we arrived at Mars on February 18th, 2021. So just about 6.5 months. And this is what we call a type 1 trajectory. It's almost a direct Hohmann transfer. So Earth was here at launch, and then we kind of did this single arc and caught up with Mars. We had the opportunity for 6 course correction maneuvers. That's what the TCM stands for, trajectory course correction maneuvers. We only actually needed to do 3. By the time we did the third one, it actually set us up so well that we didn't need the last 3. We came in extremely well into Mars. So it's about a 300 million mile journey from Earth to Mars. By the time we get to Mars, the time for light to travel from Earth to Mars is about 11 minutes. So everything is planned out based on that, and things that happen faster have to be completely automated, including entry, descent, and landing, because entry, descent, and landing happens really fast. What we call entry is when the vehicle hits the top of the atmosphere, and from that point all the way to the surface is generally only about 7 minutes. So when it takes 11 minutes for light to travel one way from Earth to Mars or Mars to Earth, that's 22 minutes round trip. I mean, there's no way to joystick the entry, descent, and landing. Everything has to be completely automated on board. About an hour and a half to 2 hours before the landing itself, we turn off the transmitter to the spacecraft. So at that point, our hands are off the wheel. There's nothing that we can do in order to help the vehicle execute entry, descent, landing. All that knowledge or mitigations have to be done completely autonomously. So about 10 minutes before we hit the top of the atmosphere, that's when we jettison the cruise stage. That's what has been keeping us stable and pointed from Earth to Mars. During cruise, we actually spin the vehicle at 2 revolutions per minute, and this gives us gyroscopic stability, which allows us a lot of accuracy and really robustness, because even if our sensors go bad a little bit, fundamentally we'll still point in the same attitude, so we can actually gives us a lot of recovery time. But we can't use that stability going through the atmosphere. So about 10 minutes out after we jettison the cruise stage, we actually despin the vehicle, and then we separate some balance masses. Now, when we're spinning during cruise, we have to have an entirely balanced system. But when we reach the top of the atmosphere, we actually create a lift vector, and we fly the capsule like an airplane through the top of the atmosphere. So we jettison some balance masses, create a lift vector, and we're actually doing a series of S-curves in the atmosphere in order to correct our distance, downrange distance to the target. So that's what this hypersonic aero maneuvering is about. Once we get through peak heating, we're actually doing these S-curves in order to make sure that we're the right distance away from the target. Once we hit the right distance, we deploy right distance and velocity, we deploy the parachute. And we deploy it based on how far away we are from the target that we're trying to get to. That's what the range trigger is called, and I'll go into a little bit of detail of that in a little bit. After we're on the parachute and all the dynamics of the chute deploying, which is a massively intense experience on the spacecraft, is basically a series of explosives that fire to deploy the parachute in under a couple seconds. Once we've stabilized from that and the vehicle has stabilized, we jettison the heat shield. Now all of our surface relative instruments can actually see the ground, and we see the ground in a couple of different ways. First is the traditional radar. This is like holding your hands out and feeling how far away from the ground you are. For Mars 2020 Perseverance, we actually added a camera-based system called terrain relative navigation, and this allowed us to use cameras to take images while we are on the parachute and compare them to a map and localize where the spacecraft could autonomously localize where it was with respect to a map on Mars, so it knew where it wanted to go. So once we were getting close to our backshell separation, the point at which the parachute wouldn't slow us down anymore, the vehicle figured out where it was and then looked at the map on Mars to find what was the safest place that it could get to based on where it was and what fuel it had available, and generated a trajectory of how to get there. So at that point, we cut the backshell, flew out from underneath the black backshell towards the target that we had picked out using this jetpack, this power descent vehicle. Once we're above the spot that we picked, the rover separates from the jetpack on a series of a triple bridle, a series of 3 bridles that lower it. It deploys the wheels, so now the wheels are no longer tucked up inside. They're down, wheels down first, and it lowers it until those wheels make contact with the ground, and you can sense the offload on the bridles, that now the ground is holding up the rover instead of the bridles. At that point, the power descent vehicle, the jetpack, cuts the bridles and then flies away and crashes a little bit, a few hundred meters away from the vehicle itself. So this all happened on February 18th, 2021, and I want to show my favorite compilation video of that. Let me see if I can get this to share with the sound. Hopefully this plays the sound also.
Propulsion, go. EDL phase week, go.
We have deemed Perseverance ready to execute entry, descent, and landing on her own.
Confirmation of entry interface.
Perseverance is currently going 5.3 kilometers per second, about 120 kilometers from the surface of Mars. It will start controlling its path to the landing target. Parachute has deployed and we are seeing significant deceleration. The heat shield has been separated. Perseverance now has radar lock on the ground. The back shell has separated. Skycrane maneuver has started, about 20 meters off the surface.
Tango Delta, nominal.
Touchdown confirmed. Perseverance safely on the surface of Mars, ready to begin seeking the sands of past life.
That always gives me goosebumps when I watch it. That video actually has the footage of the rover and the powered descent vehicle, the live footage of what it looked like on Mars to actually get those streams back. So it's the first time any mission, any of the rovers could actually captured what that landing looks like from the perspective of the rover. You know, previously we'd always gotten the data back, the ones and zeros of what landing looks like, but it's nothing compared to the actual videos of what the parachute deploy looks like and what the rover actually looks like when it's being lowered onto the ground. It was just a culmination of so much work that was awe-inspiring to see. So there were two technologies that I mentioned of what upgrades that we had to make to Perseverance to actually fly this mission. You know, going to Jezero Crater in a super hazardous area had never been done before. That actual landing site had been considered for previous missions, but had always been deemed too hazardous to attempt. I think when Curiosity considered it, it only had about an 80% chance of surviving the landing because of all the hazards of the ground itself. So there was two big upgrades that we made in order to allow Perseverance to land safely on in Jezero Crater. So one of them is called the range trigger. So when we deploy the parachute, as we transition from the entry phase to the descent phase, we have to encode the logic of when to deploy the parachute. We can't deploy it too fast because it has to be within the Mach number that the parachute is spec'd to. We don't want to deploy it too late because then we don't get the full benefit of the parachute slowing us down in the atmosphere. And that logic is always tricky to understand because we have some models of what the atmosphere and what the winds are like on Mars, but it's through each of these landings and through observation. So there's uncertainty around it. So it's a matter of what do you rely on as your uncertainty. The previous missions, Curiosity in specific, used a velocity trigger. So they basically just said, okay, we know the bounds of our parachute in terms of where we need to deploy to make sure that it works. So we're just going to base it off of that velocity trigger. Perseverance went to a velocity constraint range trigger where it actually used its knowledge of how far it was from the target to deploy the parachute. So it wouldn't deploy it early enough, it would deploy it based on how close to the target it had gotten. This was a one-line change in code that allowed us to reduce, to improve the accuracy by over 40%. So you can see the blue line here is what Curiosity's velocity triggered landing ellipse looked like, and the equivalent of the range trigger ellipse is this yellow line here. So just by doing that one line change of code, we were able to knock off all of these different areas, which for Jezero Crater is super important because all of these have the rocks and the cliffs that if we can ensure that it stays within the yellow circle 99% of the time, we can make sure we have a better ability to place that yellow circle in a region that's optimized for landing success. The second technology was called terrain relative navigation. So this consisted of two big parts. The first one is a new sensor that we developed called the Lander Vision System, which actually uses a camera to take images of the ground, has a new computer with an FPGA that we use to process those images really fast to correlate them between the images and an onboard map that we had in order to localize the position. Once we had the position, we had another map that we called the Safe Targets map, where we used orbital imagery and actually hand colored each pixel to understand the hazards of that pixels, where blue is the safest and then red is varying degrees of death. So when Perseverance actually came in, the white line here is its approach into Jezero Crater. So it ended up, we tried to aim basically in this middle, in this blue area, but we ended up coming in a little bit long. So we were in these rocky fields down here. So it really helped. It was essential that we had this technology, because what terrain relative navigation was able to do is, amongst all of these different rocky regions, it picked the safest place that it could get to inside these. So threaded the needle between all of these different hazards in order to land safely. So a little bit more details for those of us nerds who like all the technical jargon of how the Lander Vision System works. It's a two-part estimation scheme, where the first part is a coarse landmark matching, where it takes 3 images in succession and does a batch filter processing on those images. About 5 features per image, that you get 15 samples across these 3 images, and those are used as a batch filter to estimate what the pose of the spacecraft is in the position. So that batch filter allows us to remove the initial error that we're flying in with, which is about up to 3 kilometers of knowledge and certainty error. After we're able to come up with that coarse solution, that seeds a fine landmark matching phase, which is basically 100 little templates that we use to pick out and compare between the image and the map, and that allows us to really hone in on what the position is, because now you have 100 different spots that all have to line up exactly in order to come up with one solution for the spacecraft. So that lets us actually go from about 200 meter accuracy at the end of, in terms of knowledge, at the end of the batch update, to about 40 meters position error at the end of each of these fine image updates. And we do this throughout the parachute phase, and then the spacecraft uses a solution at backshell separation when it plans its divert. So for the coarse estimation phase, we take the descent image. The algorithm autonomously selects landmarks based on a heuristic approach out of that image, and then it cuts little templates out of that, warps them to the map, and then normalizes them. And it takes the map image, normalizes that, and it basically does a FFT correlation between the templates from the descent image and the normalized map, and that correlation basically shows up as a peak, and that peak is where the two match the best, the descent image and the map. So that allows us to hone in on the accuracy. So this circular gives you a visual impact of that. So when we come into this process, we have an uncertainty of the vehicle position of about 3.2 kilometers. And by doing this process with 3 batch images, we get it down to about 200 meters. So that's the little pink dot here. That same process is done also with the find position, but now instead of just 5 features, you have about 100 of these tiny templates that you're doing. And you take these templates and you search over that find map that's been normalized to get that spatial correlation. And then you put that in an extended comma filter that's propagating that state between images using an inertial measurement unit. And it basically converges out into a solution of what the position is. So we get from about 200 meters going into this fine estimation position to about 40 meters or better at the end of this. So the last thing I want to show is a video of the actual telemetry that we got from landing day of the lander vision system. So just to give a little background, the one here on the top right, that's the actual descent image that we got from the camera on landing day. The bottom right here, that's the whole map itself that we stored on board to compare against. The blue square here is the zoomed in portion, that's the big leftmost image. And then the red trapezoid, that's the image footprint. So that's what you see here on the right, where this dotted line is the leftmost portion of the image here. The green squares are those templates that I talked about that are comparing between the image and the map. The color coding of those squares indicates whether they were good matches or bad matches. So the green or blue means very good matches. Those were the ones that were actually used. And then the other colors like red, pink, yellow, and orange were landmark matches that the algorithm thought were outliers. So it threw them out of the estimation scheme. Okay, so let me start this. So here we go. Ooh, we already went fast to the fine matching phase. So we can see the vehicle is actually descending as it's taking this. The red square is coming closer and closer into the map. Now we're starting the divert itself, so you can see all the features are going off on one side. This is because the camera image is actually tilting because the vehicle is doing its descent. We're still able to match through that actually, and you'll see eventually it comes back all the way around, and it's honing in on the eventual site that we selected, which is kind of in this region. So we started from the large scale, having features everywhere, to the small scale right above the landing ellipse itself. Let me see if I can get it there. So this is the coarse match phase. It's only for 3 images. You can see big templates, and then it goes into the fine match phase. So this is the actual telemetry of how it performed on Mars. You know, we had a spectacular day in terms of accuracy of landing on Mars. That initial position uncertainty that we thought could be up to 3.2 kilometers was only about 200 to 300 meters going into that. So it allowed our estimation of it to start with a very good prior estimate. So at the end of the day, after 300 million miles of going from Earth to Mars, we landed within 6 meters of the target that we selected to land on Mars. So it was just phenomenal to get to that level of accuracy of landing on Mars. You know, we had aimed for something more like 60 meters, and across all scenarios, all bad days, we were aiming for making sure we could land towards 60 meters. So to be able to see it land to 6 meters at the end of the day after a 300 million mile journey was just phenomenal. And I just wanted to do a shout out to the whole team. You know, there was a massive effort here, not just with the people at JPL, but all across the world. You know, we had almost half the NASA centers participating in the entry, descent, and landing, NASA Langley and NASA Ames and Houston. We had instruments for Mars 2020 contributed from multiple different countries, vendors that were all over the United States that helped build pieces here and there. So it was a remarkable team effort, incredible team effort, because every little bit was necessary, and there was no one organization, whether JPL or NASA, that could really do all of it by themselves. And then just to close, this was our last picture that we took about an hour and a half before landing. It was taken about 15 minutes before we had to go in for our final butts in the chair, not allowed to leave until landing is done moment with our lucky peanuts. And with that, I think I can stop and open it up for any questions.
Yeah, thank you so much, Swati. That was terrific. It is a goosebump moment when you watch that video. It's just terrific. Yeah, we'll have some questions here. Folks can raising hands. If you want to type them in the chat box there, we can put it. One, it puts it on record too, so we can kind of see it. But also, we'll call on you. So Cal Powell, you want to ask your question?
Yeah, hi. Ingenuity recently took a close-up look at the back shell and the parachute. Did you learn anything from that image?
That was an incredible experience, and we are still analyzing those images. You know, we've not over-designed, but we've designed our heat shield and our parachutes and back shells based on the information that we've had from previous, but we've never gotten any data after the fact to know how they perform. This is the first time we've actually seen images of what they look like afterwards that we'll be able to compare and say whether or not the design factors we had were sufficient, what we can learn from those images. So I know those data are being thoroughly analyzed. A lot of that analysis actually comes from our partners at NASA Ames, because they're the ones who support a lot of the aerothermal effects portion of what we do for entry, descent, and landing.
Thank you.
Is there anything to be learned from the crane itself that flew away? I know that's not really part of the aerodynamic mission so much, but
you mean the powered descent vehicle?
Yes, right.
Did we? I mean, I would love images of the powered descent vehicle, but the purpose of the parachute and the helicopter, taking pictures of the parachute and the back shell specifically, was to get information of the design factors for the back shell that we could then feed into different missions. The next set of missions for Mars Sample Retrieval Lander is looking more like it will be a lander, not a rover. So they actually won't have a powered descent vehicle. It will be a physical lander that will go all the way to the surface. So the criticality for the next mission of looking at the powered descent vehicle is not as much, because they fundamentally won't have one.
Okay. Let's see, John, do you want to ask your question? Not John DeRosso. Birch, John Birch. Or we can go to Chris Kagi.
Sure. So as a civilian, it was thrilling to see the video of the actually live video from another planet come down. As an engineer, was it useful? Was it terrifying? Was it just eye candy to keep Congress happy so they keep sending money? How did you watch that? I mean, you had a different set of eyes and a different.
Yeah, I had a very unique perspective, right? So it was not eye candy for me. I mean, that stream was done live as we got the data down. So when I was calling out what was happening, it was live as we were seeing it. So the 7 years of what we had built to get to that moment, and the over 500,000 lines of code, over the 50 pyrotechnic devices that had to go right, and all of the knowledge that we had in the system, not just of how we thought that it was going to work, but all of the places where we knew it didn't work quite as well as what we wanted to. And we made decisions based on risk of how critical we thought that part was, what was the likelihood of it getting to that part. All of that came and like culminated in that minute. So when I was calling out what was happening, what I was hearing is the shorthand, the entire entry, descent, and landing team, as they were calling out one event after another in our checklist of everything that had to go right. So it was incredibly thrilling, and at some level not fully internalizable, at least by me, until much later in the fact, because they were so focused on just the events that were happening in that second that I didn't really grasp the enormity of it until after it had landed. And it really only started once we got that first picture back from Mars. That was the screenshot, because up until then we had practiced, we had practiced that multiple times in that same room to make sure that everyone knew what they were saying, that we could read it out fast enough. We'd even practiced it when our teammates were pretending to be gremlins and throwing issues at us to see how fast we could triage that. So it was only, and at the end of that, it would usually be a picture of like our testbed engineers holding up two thumbs, to signal the end of the test. But that was the first time where we actually saw the image of Mars, saw it as we expected it, with the rover right side up, with the amount of rocks that we would have expected in a safe area. And that's when it started to hit home that we actually did it, that all of the pieces that had to go right, stuff that we'd been working towards for 7-8 years, almost my entire professional career at JPL to date, actually worked, and worked well.
And now, not to underplay the emotional significance, which is huge. Is there science that you're able to have come out of those videos, or other engineering efforts that are able to come out of those videos that you wouldn't be able to do just with the regular telemetry?
Absolutely. So the videos, especially of the parachute and the rover download, that's the first time we've actually been able to see that. The parachutes are always a tricky thing because we can't entirely create the same environments here on Earth that we get on Mars. So we always have to do this extrapolation. And up until now, we only knew whether or not it worked by like measuring the velocity, but we didn't actually know the deployment dynamic. So with those images, we can actually finally have deployment imagery, high rate imagery of what that parachute looks like, and can compare it to the models that we had here on Earth, and the test data that we had in wind tunnels, and test data we had in high altitude testing, to be able to correlate and have a better idea of what the dynamics are. For the surface-based model, one of the big things that we were always worried about is, as we were descending, the interaction between the rocket plumes and the ground, of how much debris it sends out and how much that would get back on the rovers, what that flow would be like. We don't have good surface models of Mars because each area is different. Each rover is different in terms of its mass. So actually getting visual data of like how fast those plumes are moving out, what that looks like, what the backlash is of those, like whether they're coming back or not, that was super helpful for us to be able to triage how to tune our instruments to be more robust to that in future landing missions.
Wow, super. Thank you so much.
Okay, I want to skip a couple questions and we'll get back to them, I promise, but I want to go to GMU, see how those guys are holding up, and they had a question too. So Robert or Mike or Alan?
Yeah, you kind of went over a lot of basically my question, which is how much of that entire sequence was physically tested on the Earth, and how much of it was simply extrapolation or mathematical modeling?
There is no way that we can physically test the end-to-end entry, descent, and landing on Earth. It's just not possible. So what we do is we have a piecemeal approach, what we call the trifecta of the verification and validation. 3 different aspects that serve to cover that that scope, because we can't test it entirely here on Earth. And the 3 different aspects are dynamic modeling and simulation testing, hardware bench testing in our mock-ups, and then field testing. So the the first aspect of the dynamics modeling testing, we basically create simulations, Monte Carlo simulations that disperse all of the different environment models and noise models and parameters, and run simulations of what entry descent and landing looks like across like 100,000 different instantiations of landing day. And this allows us to see the spread of how our system is designed, not just in the nominal sense, but in the tails at that distribution and bad day scenarios of what it means. It allows us to catch a lot of those interactions that we don't necessarily know, and to tune our system, you know, based on the Mars atmospheric cycle that we're landing at and the gravity location of where we're going. Like, how do we tune the timeline to get the robustness that we want, so that it's optimized for a wide variety of landing situations. The second is benchtop testing. So we have mock-ups at JPL, engineering models that are form, fit, and function identical to the flight vehicles that we use to run the actual software on the actual processors that will be used for landing. And in some scenarios, we have actual sensors, and we use the hardware in as much of a flight-like environment as we have, and then hook up simulated inputs to it. So we have a dynamics engine running that will fake in data to the sensors and the processor to make it think like it is on Mars. And that allows us to catch hardware software interactions, things like making sure we have enough memory, that we didn't have any process coding errors that would cause the processor to reset, that the processor is fundamentally able to handle all the transactions that we wanted to give in the timeline that we have to give. Because a lot of these are, you know, sub-second level accuracies of how fast that they need to do. We actually run our cycle engine at 64 hertz. So that's 15.6 milliseconds. And that's how fast these things are clocking out, that we need to ensure that they're at that the latencies and things like that all meet within expectations. And then finally, the third one is field testing. So this is the one where we try to put the sensors or the hardware in as much of a Mars-like environment here on Earth to flush out any unknown unknowns. So like for the parachute, we put the parachute in wind tunnels. We take it up in high altitude balloons to get to a similar density, atmospheric density to Mars, and deploy it there to make sure that we understand what it's going to do. We took our lander vision sensor out to Death Valley and flew the camera over Mars-like terrain out in Death Valley to make sure that that there weren't things that we hadn't thought of in terms of how the sensor behaved, how the individual pieces behaved when you put it into a similar Mars-like scenario. You know, we took our pyrotechnics out and deployed them to make sure that they could eject the parachute how they expected to. And then we took the data for that and refined our models in both our dynamic simulation and in our hardware venues to be as realistic as possible. And then we were able to run a lot of scenarios based on that, both for nominal runs as well as off-nominal, where we'd purposely inject different errors at different points to make sure that we could recover for them. That was all getting the spacecraft ready for entry, descent, landing. And the last couple months before EDL, we got the people ready for entry, descent, and landing, where we actually did operations readiness tests, where we put everybody in mission control who's supposed to be there and made sure that they knew what they were doing. They had their processes, any calculations that they had to do for last minute parameter updates to the spacecraft or trending, that we worked through all the bugs there so people knew what they were going to do, knew what they were going to call out, such that on landing day, we didn't have any issues from there. And we were as prepared as we could be, that if something happened on the spacecraft, we could react immediately.
Thank you. I have to say that entire process is phenomenal, beyond phenomenal to me. Like, that is, like, landing on Mars is awesome, but that process, the fact that we can do that and it matches up with reality is, I don't have words for it. It's amazing.
Yeah, it really is crazy. Let me go back now to, let's go to Steve. Steve had a question. I'll get to Jay here. Just give me 1 second, Jay. So let's see. Steve had a question.
My quick question. I know that there had to be a lot of pressure on this already. Did y'all have any extra perception of pressure or extra feeling of eyes being on you, given everything with the pandemic and knowing how much people were cooped up and watching things? And did that put any extra awareness or pressure or anything, or was it just too much already?
The pandemic did put additional pressure, though the public perception of it, I don't think we really felt too much. I mean, a lot of our team was shielded from that. The media team does a good job of handling most of those. But because of the pandemic, we had to rethink how we did operations fundamentally at JPL. You know, the modus operandi before that had been just get everybody into the same room in mission control, then you have everybody there, and if something goes wrong, you have all the people that you need. That wasn't an option anymore. So now we actually had to start making decisions of like, well, who do you actually need there? You know, how fast can you get a hold of people that you need? What's the risk benefit, and how to manage people coming on lab, because every individual situation was different. So having that added burden of having to actually weigh personnel safety against the spacecraft safety was definitely a new layer of added stress and challenge for flying this mission.
Well, it sounds like y'all were well shielded from kind of the public pressure, but just to let y'all know that it was an amazing bright spot, you know, during all the pandemic stuff. Being able to watch that was just wonderful. So thank you.
Yeah, I think we got a taste of it on the flip side. So I think going into it, we didn't really feel it, but I definitely saw it from the flip side of suddenly how it just, you know, kind of blew up after landing. It was a confluence of events of a landing that was more or less in the middle of the day, you know, for us. Like the previous landing had been at Curiosity was like 11 p.m. for Pacific Coast, so it was like 3 a.m., you know, 2 and 3 a.m. for East Coast. So not a lot of people, but this was smack dab in the middle of the day. Everybody was more or less at home also for this, so they had the ability to watch. Even like the schools, like my daughter's schools, they stopped during their lunch break and had this on streaming. So we got to the point whereas we didn't realize how many people it had touched until after landing itself, and kind of the world blew up with it. Really happy that I went. It was a success. We kind of really needed it at that point.
Yeah, I mean, it was just totally galvanizing. You probably didn't appreciate it, but now that you see it, I mean, just you can even in your video, the whole world was like excited about landing on Mars. I mean, it was, and you know, everyone needed it too. So I mean, it was really tremendous. Let's go to Jay Birch.
Hello, thank you very much. I had several questions, but the one that praised mostly has to do with the theories or models that people have developed about the possible evolution of previous life on Mars, how the planet itself evolved, and what kinds of life sign density might there be on the surface of Mars after, you know, whatever erosion is occurring and all that, and then comparing that against the sensors that you're able to develop to detect any such signs.
And so I have to preface it by saying I am not a geologist. I'm a controls engineer. So most of what I know comes from talking to the other scientists on Perseverance. But from what I understand, the features that they're looking for are very a specific type of rock that has this type of knobby formation where that processes to create that is caused by microbes. So it's and it can only be created in that type of knobby, like very angular jetting formation by that life process of microbes eating it and kind of secreting it into that formation. Anything else in terms of geologic features like wind erosion or water erosion ends up making like very smooth features. So that type of knobby rock or knobby formation is one of the things that they're looking for on Mars, because they can find evidence for that particular type of rock. It's basically it's a fossil of this type of microbe processes that is a life-based process for creating this rock formation.
We have those on Earth, and
we have those on Earth. Yes, so they actually, the science team went to different areas of Earth to try to learn from how those formations and use that data to make sure that the instruments that they picked had, you know, the features to be able to look for that type of geologic feature on Mars.
Okay, the other question is maybe more along your line. During the descent, presumably the sensors were recording information about their own latency and how, the rate at which descent occurs based on your predictions of the parachute behavior and the shield behavior and a lot of other things. How much of that data has allowed you to change, or what did you learn from that data about the descent that you might use in the next in the recovery mission?
Yeah, so we actually did get pretty much all the data that we had recorded back on Earth, and we spent about 8 months poring over that data, and it was presented at various different conferences. Each little module, so to speak, of that entry, descent, and landing had its own things that it learned or didn't learn. Some of them, so I was in charge of the landing accuracy budget, so we were able to basically take our pre-launch estimates of what we knew then and how much we had ballparked to cover certain regimes to our in-flight estimate, but that was before landing, of okay, now we're in space, we know, these 3 variables post-launch, and then actually do a reconstruction of what we got on the ground. And that's one example of it. Helped us learn how much of our tools and simulations were accurate. So we were basically able to say, okay, with these inputs that we know best, let's run our tools and see what they would predict and make sure that they were able to predict what we actually got, because that's one way of validating our tools that would then be used for the next mission. And then the second one, it allows us to understand whether or not our assumptions are good in certain places, especially for the first time things like the terrain relative navigation. We made engineering judgments on certain assumptions to make sure that we could cover a wide range of scenarios. And with the data that we have for the one run that we have, we're able to correlate that and see, okay, how many of the assumptions that we put in there actually panned out and were useful for adding the margin where we needed to at the time.
Okay, let's go to, let's see, a couple more questions. I know we're going to hold you over just a few minutes, Swati, but John, do you want to ask your question? John?
Sure. If when I was looking at your data, at one point it looked like where I thought you wanted the rover to land was this very flat area just on the other side, I guess. Not sure which way was north, but southeast of a cliff. But then you showed a line that said was pretty long line of where the rover was actually going on its true flight path, and that looked like it was hundreds of meters away. And then later you said, well, we were only 6 meters off. So is that 6 meters from an alternate site than the primary site, or how do I interpret that?
Yeah, so for the landing ellipse, we have a target that we fly in from space, and the center of that target is the center of the landing ellipse. So as we came in from outer space, we were aiming for the center of that target. So when we actually came in, we were going long, but that target isn't where we would end up landing, because the vehicle had what we call safe target selection. So as it was coming in, at the time that we were ready to cut the back shell, it was going to decide on the fly, based on where it was, what the safest spot was around it. So it, based on the location it was at the time of us jettisoning the parachute, it looked at the map that it had, found where it was, and then drew a circle around it and said, okay, based on my fuel, I can reach this area, and did a search to find the safest spot in that region and then aimed for there. So when I say it went 6 meters from where we picked, it's that target that we picked on the fly based on what the safest location was as it was coming in. So we landed 6 meters from that. The target that we had aimed for coming in from out of space, we did actually fly long, a couple of 100 meters long, and ended up farther into the southeast portion of the landing ellipse. That was due to, fundamentally comes out due to uncertainties in the way that we had set up the interaction between the entry vehicle and the atmosphere itself, kind of propagated down into flying a little bit long. So we ended up in a region that was actually more hazardous than what we call the landing strip. The landing strip was that nice blue strip right by the cliff, right on the other side of the cliff. That's actually pretty flat and nice. We were hoping to land somewhere there, but we flew past it basically on our way down. So we had to decide on the fly. When they decided on the fly, it was actually farther into that rock fields on the southeast that the rover picked to go to. And then we ended up landing 6 meters from where the rover actually aimed to go based on what it had decided was the safest spot.
Okay, great. That makes perfect sense. Thanks.
Yep. Thanks. Let's go to Sentil. Just a couple more questions, if we can. Let's see, Sentil and Navin. You guys had questions?
Yeah, thank you so much for the opportunity for the question. How far did the Perseverance collected data from the landing site? So just curious to know more.
So Perseverance has been driving quite a bit from the landing site. It hasn't followed a very straight path. So from what I remember, it's gone a little bit north and kind of gone a little bit out, and is trying to go up that inlet channel of that river up to the cliff. So I don't exactly know how far it is from the landing site, but it's definitely traveled hundreds and hundreds of meters at this point.
Okay, so they are planning to drive up that river channel if they can get to that.
Yeah, it's not clear when that will be, because there's a bunch of different factors at play, like where they want to take the next set of samples, or where the next Mars landing will go, and whether they want to be up on the top at that time or still down in the basin. So it's kind of a multi-agency decision of when to go up and where to go up. But the eventual science is to kind of drive in that northwest direction.
Okay, I'm going to end with Dan Ward's question, but I want to see if Jay, did we cover your questions, or did you have a follow-up?
I did. I was curious about seismic measurements. Does the rover have seismic sensors, and might it have been able to determine more of the underground structure from the impacts of the extraneous equipment that was jettisoned on descent?
Well, even if the rover had it, the jettison of the equipment would be happening simultaneously, so it wasn't really in a position to measure any of the impacts from the hardware of its own landing. Perseverance doesn't have as much seismic instruments as other missions. Like InSight has the most seismic. That's kind of its main purpose. And Curiosity did have a ground penetrating radar, but Perseverance doesn't really. We tried to look at some of our rover IMU, inertial measurement units, to see if we could see the crash of the back shell, but it was a little bit too noisy to see. There might have been something from InSight that saw something, but I don't know if we've actually looked at that data or not.
Okay, we'll go. Any last questions from anyone that hasn't typed something in? Jay, we can't satisfy Jay enough. You have another question?
Fascinating. Yes, I do. You said something about the material recovery mission not having a rover. Is that correct?
It's not quite clear yet whether the sample retrieval mission will have a rover or not. There are kind of multiple different options. At the very least, we know that the next mission will have a lander, and on that lander will be a rocket, because that's the rocket that's needed to get the samples into and then launch off of the Martian surface.
Ah, okay, that clarifies. Thank you.
Okay, then I think finally we'll go to Dan Ward for kind of the send-off question.
All right, thank you so much for this wonderful talk tonight. Your team has done something incredible, and in the other world it would be you've won the Olympics, but this is so much more important than any Olympic medal. But and certainly there's a lot of follow-on. But what do you see? What's your dream next big project?
I don't know, actually. I'm still thinking about what that dream is afterwards. I am helping out on the next couple of missions right now for JPL. So the next one is next one that's up to bat is Psyche, which is a mission to a metal asteroid in the asteroid belt. And then the one after that is Europa Clipper, which is a mission to the moon of Jupiter, which we're super interested because we think it's one of these ocean worlds that might have a subsurface ocean, which also be a potential for life. And then the next mission after that I've been helping out with is the Mars sample retrieval mission. So that's the lander with the rocket on it to get the samples back from Earth. And that's a kind of the next the follow on to Perseverance, because Perseverance is picking the samples, but we have to get those samples back to Earth. And this would be the mission to actually be the first to launch a rocket off of Mars, which has never been done before, and we'd have to land basically to pinpoint accuracy to get right where the samples are, because it's going to be a lander, not necessarily a rover. So the closer we can get is the capability to get those samples. So that's from the technology. That's really an augmentation to get from where we were on Curiosity to Perseverance to now sample retrieval lander that has to pinpoint land on Mars after that entire.
Thank you so much for your dedication and your service to humanity.
Thank you.
Yeah, I mean, thank you. I just echo what Dan said. I mean, dare mighty things. It's kind of one of your mottos, I know, for the program. And boy, you and your team certainly have done that. And we've all benefited from it. And just to experience that and relive it through videos and through experiences like you're sharing with us tonight. I mean, thank you so much. We'll follow your next steps, and we'll all be interested for the future successes. So thank you, Dr. Mohan, for being with us tonight. And for all of the rest of you, there's a lunar eclipse going on. I haven't checked the weather. I think maybe it'll clear a little bit later. So, and maybe on the West Coast, it's going to be clear. So that's something cool to go look at. And thank you so much for the outreach for all our members. And there's lots more to follow. So take advantage of that and help us out, sign up. And we'll see you at Astronomy Day and Viva Vienna. So thanks, everyone, and have a good night.